I'm David Pellerin. I've been with AWS for 5 years now and focusing primarily on high-performance computing across industries. So I'd like to share with you what HPC means to many of our customers, what some of the use cases are, but more importantly, some of the technical enablers and how you should think about deploying HPC on AWS. So again, we'll survey the applications. What does it mean to be HPC? That's kind of a term with a lot of baggage, if you will. Some people may think HPC means one thing, other people think it means quite another. So I'm going to talk about how we define HPC broadly. I'm going to talk about best practices. So as you begin to deploy high-performance applications, HPC applications on AWS, for example, large-scale simulations, financial simulations, for example, engineering simulations, deep learning, which we really should categorize as HPC. What are some of the performance best practices? I'm going to talk about accelerated computing because that's becoming incredibly important, both GPUs and FPGAs. What we're seeing in applications and also the instance types and some of the supporting technologies that we have. I'll talk a bit about automation, how batch fits in, how traditional HPC schedulers can fit in, and I'll also talk briefly about graphics. So when we think about HPC, high-performance computing, that really means doing something with vastly more compute than is generally delivered by a single CPU or CPU core. And there's a wide variety of applications, and I like to kind of characterize them in this two-axis graph, right? So many legacy HPC applications are dominated by network, they're dominated by interconnect, they're dominated by messages that have to be communicated between different tasks in the HPC job. And so those are the ones at the top of the chart here. So fluid dynamics, for example, or structural simulations, weather simulations. These are traditionally HPC codes that you find running in supercomputing centers around the world that are really dominated by network performance. And if you go to the bottom, these are grid computing workloads that tend to be embarrassingly parallel or pleasingly parallel, right? They don't require so much network traffic. And then you go left to right, and that would be data intensity, right? On the left side, you don't really have a lot of data that you need to deal with on the particular problem. At the extreme would be something like a Monte Carlo simulation used in the financial sector. You just feed a few values in, you crunch, 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 you get some values out at the end. Or data heavy on the right, and these are things like animation rendering or seismic processing or semiconductor verification where there's lots of data to be dealt with, and so you need to have high performance storage. So this is how we kind of characterize. If you go back to the early days of cloud, the low and to the left were obvious candidates to bring in and scale up massively, and there was lots and lots of those workloads brought into the cloud quite quickly. Now though, we're seeing applications throughout this that are enabled by capabilities of AWS on the compute side, on the network side, on the storage side. Really tremendous migration now of some of these workloads to cloud that we would formerly have considered kind of exotic HPC applications. So the important enablers for HPC, however you define it, you've got to have high performance compute. That's at the core of HPC. So that can mean CPUs, it can mean accelerating with GPUs or now even FPGAs, and getting access to lots and lots of them when you need them. Increasingly, HPC problems that we're seeing in the commercial sector are dominated by memory, so more and more memory being required for some of these problems. So we need to have high memory instances that also have high CPU performance. And network, it can be very, very important for those tightly coupled workloads. And network performance can mean throughput, it can mean consistency of latency, and it can mean low latency. There's lots of different factors that come into the networking performance. And then storage, of course. Storage can also mean high throughput from the data source into the application, or it can mean high IOPS, right? We're smashing a file system to get lots of little tiny files in. So storage, you need to have lots of options there. HPC also requires automation because typically these are very large batch jobs, or if they're interactive jobs, you need some way to orchestrate all of the compute that's happening behind the scenes. And then if you want to do full HPC, meaning from pre-processing to post-processing, you also need graphics capabilities. And for HPC, you need scale, right? So It doesn't really help to have all of these things if you just have a desktop PC or you've got a few servers in the back room. Scale is what really drives HPC on the cloud. Ridiculous levels of scale. I want to briefly touch on this idea of loosely coupled versus tightly coupled workloads, that vertical axis of the graph I showed earlier. Clustered HPC, those are things like your fluid dynamics simulations and structural simulations, weather simulations, many other types of solvers, electromagnetics, for example, that require lots of network performance. They're very chatty, if you will. So consider those to be cluster HPC, tightly clustered, tightly coupled workloads. For those, capabilities on EC2, like placement groups, enhanced networking, optimizing the use of, for example, an MPI library that's well-tuned. Those are very important to get performance for cluster HPC, for traditional legacy HPC workloads. Grid HPC is those pleasingly parallel workloads. For example, the Monte Carlo simulation in finance I mentioned, right? Or maybe genomics or other types of workloads in which the network is not so important. It's more about getting lots and lots of CPU cores or GPUs. The best strategy when you're thinking about scaling on the cloud is to think about creating grids of clusters, right? Perfect example of that would be doing a fluid dynamics simulation that maybe takes 100, 200, 1,000 CPU cores for one job. But now I want to run lots of jobs in parallel, right? So think about using a grids of clusters methodology for this, right? So create maybe a placement group using enhanced networking for one job, and then repeat that, maybe even using different availability zones to spread that workload out and scale it up. So I want to show you some specific examples from customers, and then we'll dig a bit deeper into specific best practices. First, in the public sector, the Large Hadron Collider, a great example of where big data meets big compute in a big explosion, if you will, right? So the Large Hadron Collider, when they run an experiment, they generate vast amounts of data. If they see interesting patterns in that data, then they need to run large amounts of compute to figure out what exactly that caused that pattern of data. And that's a pattern that we see in industrial applications as well. I found a pattern in the data, now I want to run simulations to repeat that pattern so I get at the causality, right? So what we've observed in working with partners such as Brookhaven National Labs is that they can scale these large simulations dramatically. This is a graph, this is accessible actually from the Brookhaven Labs site, showing how many CPU cores they are launching at any given time. And this is back in January of last year after one of the runs. And you can see they begin to scale dramatically using spot instances, multiple instance types across availability zones, across regions, and they're peaking at 60,000 CPU cores. And you know, so sometimes it goes back down to zero, sometimes scales back up. But this is a pattern that we see now again and again, also in the enterprise space. Vast numbers of CPU cores being spun up and spun down on demand as needed. And again, this is a pleasingly parallel job. It is also a stochastic simulation, right, for high energy physics. It's easy to spread that across many, many CPU cores. Here's another great example of a pleasingly parallel job, and this one quite massive. This is Clemson University running a natural language processing analysis problem, a really machine learning problem, right, for NLP. And you can see over the course of literally hours, they were able to scale up in one region in US East Virginia 1.1 million vCPUs, right, which translates into something like 500,000 CPU cores, physical CPU cores. That's a huge enabler, right, for a research team at a university to be able to spin up and get access to over 1 million threads of compute on demand and not pay too much for it because they're using Spot. In this case, they worked with our with Cloudy Cluster from one of our partners, right? So very exciting project there. You can read about that. It's a case study. Anyway, I wanted to share that because when you think about scale for many of these applications, you can actually think about ridiculous scale. On the accelerated computing side, The use of GPUs now is becoming much more widely accepted across industries. This is one particular case, Aon Benfield. They are a division of a global insurance organization. They do reinsurance products for other insurance organizations. They're also stochastic simulations, also pleasingly parallel, but very, very good acceleration can be achieved also in GPUs. And so they use GPUs at scale to do these large simulations for the insurance industry. And there are just so many examples like that. Earlier today, we had a session on design and engineering, and Kobayashi-san of Western Digital, which is now a division of HGST, which is now a division of Western Digital, spoke about their use cases. And similarly, a manufacturing organization like Western Digital has many, many different simulations that they perform on a day-to-day basis to design new products. Disk drives, they're actually very, very complex pieces of machinery with spinning parts and different fluids in them and so forth. They have lots of simulations to do. One of their simulations in the magnetics side for doing drive head characterization, they have, similar to Brookhaven, spun up 85,000 cores at peak, over 80,000 cores to run this one set of simulations. And that's a pattern that they can repeat on a regular basis. And they're moving a lot more high-performance compute workloads in over time. So I use these examples just to illustrate the benefit of scalability for a wide variety of industries, both commercial sector and public sector. Well, let's dive in a little bit deeper into legacy HPC, right? So legacy HPC, meaning tightly coupled, supercomputing types of applications, include things like weather simulation, fluid simulations, and so forth. And the general understanding or belief out there in the supercomputing industry is that you need particular kinds of infrastructure, particular networks and so forth to make these applications even practical. And so we've demonstrated, really beginning with our C3 and C4 instances, and certainly now with C5, with enhanced networking, that you can scale these types of workloads very well on AWS because of the consistency of the latency, because of the performance of the network that we're providing. And so what you're seeing here is a very nice scaling curve that goes right up to over 4,000 cores on AWS for one tightly coupled weather simulation. Similarly, similar graphs in structural simulation. So this would be codes such as LS-DYNA or Ansys Mechanical and so forth, right? These are workloads that are also tightly coupled, traditional HPC, traditionally requiring very high performance on the network, and they scale quite well on AWS. Last graph here on that, Ansys Fluent, one of the most popular fluid dynamics codes out there, run in aerospace and automotive. Many, many customers use Ansys Fluent. It's very well known. And Ansys did some benchmarking using our C4 last year and found excellent scalability of these codes on AWS. And so what I want to emphasize here is that these legacy HPC applications are very practical to run on AWS. They scale very well. But it is important, as we'll see in a moment, to think about best practices for optimization to get this kind of performance. Oh, last example here from our partner Rescale, who's worked with Boom Aerospace. Outstanding case study of running fluid dynamic simulations, highly parallelized fluid dynamic simulations, allowing them to do many different parameter studies, case studies, if you will, for fluid dynamics for next generation supersonic aircraft. A very exciting use case. And Rescale has many customers in this space doing these types of workloads on AWS. All right, so let's dive in a little bit and talk about performance considerations. How do you get that kind of performance? What are the things to think about when deploying HPC on AWS? So first, let's talk about those tightly coupled workloads, right? Those workloads that require a lot of network performance, that have many jobs that are communicating via messages, perhaps. The first thing to understand is that benchmarking and performance tuning should really be done with your actual applications with your real-world examples, right? There are lots of small micro benchmarks out there, but those really only test the network. It's very important, for example, if you're running a fluid dynamics simulation or an impact simulation, to start with a big model, a large mesh. Spread that across CPU cores. Get a good ratio of cells in your mesh to CPU cores. Go big, right? Those are the most useful for tuning, the most useful for understanding the total cost of running your workloads. So start big. Don't start with the really small examples. We've seen that again and again. It's very important. Related to that is the idea of domain decomposition. Now, if you're in the areas of fluid dynamics simulation and weather simulations, that term will be familiar to you. There's a certain number of cells that you're trying to model, right? And it's important to choose a good ratio of the number of cells per CPU core to the number of, to each core, right? How many cells per core? And that's an important optimization to think about. So when you're doing that testing of real-world examples, try different ratios of cells per core, different scale out of CPU cores, and see where that sweet spot is. And the sweet spot might be different depending on whether you're most focused on getting fast performance, job completion time, or whether you want to optimize the spending on EC2 instances, right? Not sort of overload the instances and use more than you need. So it's important to test. MPI libraries, also very important. Many of these applications use message passing, MPI. So there are different MPI libraries available out there. Our experience today is that Intel MPI is the most performant on AWS. And then second to that, we're working very closely with the Open MPI community to ensure high performance on AWS as well. But again, you have options. It's good to test with multiple options because testing is easy to do on AWS. And then on simple network performance, be sure you're using a placement group if this is a tightly coupled workload to get that locality, and use enhanced networking. This is particularly important if you're not using Amazon Linux, because enhanced networking might not be enabled, the drivers might not be there for you if you're using some other OS distribution. Just to make sure that you have the right libraries in there, the right drivers and so forth. And then for all workloads, not just the tightly coupled ones, be sure you're optimizing at the OS level. We've seen significant performance differences. For example, if you're running a newer version of CentOS, for example, certainly if you're using Amazon Linux, that's going to be performant. But older releases, older kernels of Linux can have a significant performance difference from later versions of Linux. So be sure you're optimizing. And this is important because there are many organizations out there that tend to qualify particular versions of Linux, and then they carry those forward for quite a long time without refresh. So it's important to make sure you're using a performant version of Linux. On the processor side, you do have the ability on AWS, on EC2, to control things like C states and P states, to do pinning of cores to thread and so forth. Those level of tunings can be helpful. And if you need more information about how to do that, we do have some best practices white papers about performance of HPC that can help you to understand those low-level tunings. From an instance type perspective, be sure you're testing with the latest generation instance types. C5 certainly now with Skylake, a very powerful instance type. Test also with C4. Test with with higher memory instances. Don't just settle on one instance type and stick with that forever. Continually re-optimize and retest. And it may be the case that different applications that you're running, different models, for example in simulation, might run more optimally on different instance types because perhaps one model needs more memory than another and so forth. So, always test with the latest and always right-size the instances for the particular problem. I mentioned before things about pinning of threads to cores and so forth. Hyper-threading may or may not be useful for you in HPC. Typically in HPC applications, we disable hyper-threading so that we get full performance for each thread running on physical cores. That can be done on AWS. It's not the default, but it is possible when you boot up your instance to disable hyper-threading. And again, we have information in the documentation online, in the HPC best practices paper about how to turn off hyper-threading. So those are some important considerations just to get raw CPU performance. And do remember, you've got a choice of instance types on AWS for these applications. The compute-optimized ones, the C family, are the ones that you would first think of when thinking about HPC applications, because they will have the highest clock speeds, the highest core densities. They'll absolutely have the, be sitting on the latest generation networks, as really all of our newer instances are today. But do consider other instance types for other applications. For example, if you need to create a high-performance shared file system that's temporary, you might stick that on an i3 because it's got all that local NVMe storage. It's got a lot of throughput to the network. That can be an excellent storage platform as a head node for your HPC cluster. If you need high memory, R4 and X1 are outstanding. They're very performant instance types. We see them used quite a lot, R4 in particular, for high-performance computing workloads that need higher memory. On the accelerated computing side, and apologies, the slide is already out of date, the P2 instances and the P3 now, P2 delivering the NVIDIA K80 and the P3 delivering the NVIDIA V100. These are very powerful instances for accelerated computing with GPUs. I'll talk about FPGAs in a few moments. That's new as of this year. We offer FPGA accelerated instances, the F1, lots of exciting use cases there as well. When you think about instance sizes, you've got choices there also. In the case of R4, you've got a total of 6 sizes. Most HPC customers are deploying on the largest instance, right? They got the full number of CPU cores, the full amount of RAM, high-performance memory. But actually, if you right-size the instance to your applications, take advantage of other instance sizes, instance types, right? It may be the case that you don't need that full box for your application. So don't just, because you're running HPC, think you always need that largest instance. Notice that we continue to increase the network bandwidth, by the way, so 25 gig on the largest R4 at this point. We continue to innovate on the networks, continue to pull down the latencies and increase the throughput. Lots happening there. So continue to retest and re-optimize over time. And one of the things that enables this, of course, is our Elastic Network Adapter, ENI, and all of the underlying network infrastructure that goes behind it. This is a very important development for us. If you watch James Hamilton's talk last year at reInvent, I think it was a Tuesday night talk, he talked a little bit about what we're doing on the network side. It's pretty exciting. So we build and design our own networks on AWS, ENI as part of this, but that really helps you to get very consistent latency, very high throughput from one instance to another on EC2, and also helps with performance out to storage. So let's talk about storage. In many HPC environments, so think life sciences, semiconductor design, automotive, aerospace, energy, the pattern that you would see is a large amount of compute sitting next to a very large amount of shared file system, right? Typically branded, expensive shared file systems, and that's really the storage strategy. Maybe they've got tape backup, but the strategy typically in an HPC shop is high-performance shared file system. When you move to the cloud, you have other options that are much more efficient and perhaps much higher performance as well. So S3 should really be your source of truth for data. It should be the primary storage medium. You can certainly create and use shared file systems, and you will in many applications in HPC, but it's best to think of the shared file system as working storage, right, as temporary storage. Pull from S3 to the shared file system, run your jobs, push back. Now, when you think about the shared file system itself, you can think about using EFS, right, Elastic File System, as a fully managed, scalable, durable file system. Or alternatively, you might instead, or perhaps with that, use a local shared file system that you create using EC2 as head nodes and filers and EBS as the backing storage, right? For many AWS or many HPC applications running on AWS that require extremely high IOPS storage, that use of EC2 plus EBS does turn out to be the best solution for your working storage. So just to summarize that, EFS, highly durable, scalable, scales up, scales down, super easy to use, has very high performance from a read perspective if you need to pull lots of data from EFS into your compute nodes. But because it's multi-AZ, because it duplicates data, there is going to be some latency penalty to the write. So if you have very high IOPS requirements, you need to slam the file system, you know, literally thousands or millions of files being written and immediately read again by some other application. EFS may or may not have the performance that you're looking for those applications. And so instead, you might consider building a file system out of EC2 combined with EBS. And you can do that yourself. I mentioned earlier a simple way to do that, just use an i3 instance and its local storage as a storage node, or perhaps use EBS with a fleet of EC2 instances that are acting as filers. Use a partner solution. These are things like Intel Luster. Avir has solutions, Weka.io. You can build it with ZFS. There's a number of solutions out there that I haven't mentioned here that deliver that shared file system using EC2 plus EBS. So you want to evaluate those based on your performance needs. But as I said, object storage, S3 is really the important enabler for at-scale workloads on AWS, at scale of all sorts, right? Not just HPC. So the more that you can use object storage, the more that you can use S3 to stage the data, to store the data long term, and then pull it into a shared file system when you need it, the more effective you'll be running on AWS, the more cost effective and the more performance you'll get. And then of course life cycling the data off to Glacier, which is quite easy to do relative to dealing with you know, backups and tape libraries in the legacy world. So to summarize that, you really should think of S3 as the core storage component of your HPC storage strategy. You've got lots of options for data ingest, of course, ranging from physical ingest with snowballs and snowmobiles and so forth, up to you know, connectors like Storage Gateway and the ability to connect to shared file systems that maybe are on-premise through partner solutions such as NetApp offers. But really, when you bring data from on-premise or elsewhere into AWS, bring it to S3, keep it in S3, pull to a shared file system as needed for your HPC runs. So building a high-performance NFS on AWS, we do have some documentation, some white paper about options here. As I mentioned, there are a number of partner solutions here. But for NFS or CIFS, you have the ability to use EC2 as the storage filers, right, as your storage head nodes, and EBS backing that in various configurations as the storage medium for your high-performance file system. And how many filers you have, how they're arranged, how much EBS per filer, that's tuning, right? And that'll really depend on your IOPS needs for the particular application. So let's talk now about accelerated computing. I'm really excited about this. What we're seeing now in acceleration is quite dramatic. We've been in the world of CPU-based high-performance computing for many, many years, of course predating cloud. The ability to stand up literally thousands or even millions of CPU cores has been a huge enabler for HPC across industries. But now the rapid adoption of accelerators is a trend that's helping to reduce the footprint of those HPC stacks to get results delivered faster. The best way to think about accelerated computing is a metaphor, right? So if you think about a legacy CPU architecture, Intel Xeon, for example, or really any CPU, it's a limited number of CPU cores on a die. Each CPU core has a limited number of ALUs, arithmetic logic units. It's got cache architecture. It's got data paths and so forth. It's built to be general purpose, but under the hood, it's actually a fairly limited architecture in that it's only a specific number of data widths, like 32 and 64 bits. and a limited number of ALUs that you're trying to traffic cop and bring all the data into and process. What you're doing with, but you know, a CPU is very flexible, just like a business jet. It can fly everywhere, it can turn on a dime, it can land in lots of airports, only carries a certain number of passengers and burns a lot of fuel. That's a CPU. If you look at accelerators, and this applies to both GPUs and FPGAs, it's more like that Shinkansen on the right? It's all about throughput. It's not about speed. They go fast, but not as fast as that business jet. It's more that they carry lots and lots of people on that track, right? So from a people delivered per minute perspective, the train beats the jet every time. And that's the same idea with GPUs and FPGAs. Massive parallelism. So on AWS, again, sorry the slide's not updated. On AWS, we have the P2 and P3 GPU instances, and we have the F1 FPGA instances, right? So P2, NVIDIA K80, P3, NVIDIA Volta V100, right? So these are very powerful for double precision floating point, for deep learning training, for graphics rendering, batch rendering, for example, for immersive content, for VR. That's what GPUs are very, very good at. FPGAs are very, very good at massively parallel, heavily pipelined, complex problems that may not fit in a traditional CPU architecture. For example, they can take advantage of alternative bit widths. So a GPU is really good at parallelizing lots and lots of the same instructions. And you know, the roots of GPUs, of course, are in graphics processing, where you want to have thousands and thousands of shaders, right, colors computed simultaneously. That's what a GPU is really good at. And now, with the latest generations of GPUs, that can handle double precision floating point. It can handle you know, many, many more operations, and it's software programmable. So we're seeing GPUs being used for massively parallel financial calculations, for example. And now deep learning training on GPUs, very, very powerful. FPGAs are quite different. If you're not familiar with them, an FPGA, field programmable gate array, this technology actually predates GPUs by many years. The FPGAs, as we know them now, really entered the scene in around 1985, 1986. But they've grown and grown and grown over time. The primary applications for FPGAs in the past would be things like in telecommunications equipment, network processing, anything that, video processing, anything that needs to have high-performance streaming data, embedded systems, for example. So now, fast forward, and we're seeing FPGAs being used in applications such as genomics and in large-scale analytics and so forth. I'll provide some examples of that in just a moment. But let's return to the GPU and talk about some use cases here. Now, we know that GPUs, of course, are very, very powerful for delivering graphics, for delivering interactive graphics and doing those color computations and so forth. This is an excellent example of a GPU being used, or many GPUs being used for both the graphics rendering, which is a batch problem, and then the graphics delivery, which is that interactive experience, right? This is Arteris. They were a startup that really launched on AWS a few years back, and they're now, they've got a deal with GE Medical, I believe. They're really off to the races. And this is a 4D medical imaging application. Literally, if it's running, you can see the beating heart while you twist the torso around. It's really powerful medical imaging. So what they're doing is they're taking data from medical devices, right? So CT devices and so forth, PET scanners. And from that data, they're building a high-resolution 4D model that they can then play, and the doctor then can look at the issue there interactively. And so that's a very large-scale compute problem just to do the computed tomography, if you will, from all of the data that's coming from the machines to create those imagery, and it's also a graphics delivery problem. So a great example of GPUs being used both for that high-performance compute and for the graphics acceleration interactively. Deep learning, this is a huge, huge and growing use case on AWS. We use deep learning a lot ourselves internally at Amazon, and many, many teams. and increasingly our customers are deploying deep learning technologies. And there's many other sessions at reInvent this year about deep learning, about what's happening there. Frameworks like MXNet, for example, Gluon, so much happening. But what I wanted to express here is that with frameworks such as MXNet for training, we see excellent scalability on GPUs. You just throw more GPUs at the problem, and it just scales up and up and up. So these deep learning training problems where you've got to put enormous amounts of data into that compute cluster to train the model scale exceptionally well on AWS, right? MXNet in particular, others as well. Over on the FPGA side, let's talk a little bit about some of those use cases, or one in particular that's particularly exciting, and that's genomics processing. So remember, this is not GPUs, this is FPGAs, and what I expressed before is the difference between GPUs and FPGAs. FPGAs operate on really arbitrary bit widths, and you can create complex pipelines of processing that are difficult or impossible in GPUs, right? Genomics processing turns out to be a perfect candidate because you're doing lots of processing on a genomic sequence, right? Including aligning the short sequences that you've read from a sequencer into a reference genome, for example. That's an alignment problem. You've got the need to look for variances, which is kind of a distance search problem for different genomic sequences. And genomes are really AGCT, right? Hope I got that right. They are really how many bits do you need to represent those four, genomic. I haven't slept enough last night, I guess. Anyway, you don't need 32 bits to compare one genomic sequence to another. It's a limited precision problem. Perfect fit for FPGAs. So Edico Genome is one of our early access customers on our F1 instance. They began immediately by migrating the FPGA accelerated appliance that they already had, and they were already delivering to customers as a physical appliance on AWS. So they're taking the FPGA accelerated appliance and migrating it to F1, right? Didn't take them long, but they have massively accelerated genomics processing. In fact, they had a story a few weeks back about doing a world's record genomics processing on AWS F1 using 1,000 FPGAs in parallel to run 1,000 pediatric genomes in 2.5 hours. It's pretty exciting. But it's not just genomics. There's lots of applications that fit this model of having either arbitrary bit widths, the ability to operate on reduced bit precisions, or that require some complex pipeline of processes, right? Video processing is a perfect example of that. As I said earlier, in the case of Edico Genome, they had a physical appliance that they would sell previously that they're now migrating to cloud. You're also seeing that in video processing, for example, NG Codec, who had the ability to create a physical appliance, and now they have a virtual appliance, if you will, on F1. Rift, similar idea. Rift has high-performance data analytics that's FPGA accelerated. They can sell you a box that has FPGAs that'll do that in your own data center, or they can deploy that on F1 using AWS. So many more applications. It's a really exciting area, lots of new partners. Let's talk now about deployment of HPC applications on the cloud. If you think about a legacy stack, a legacy HPC infrastructure that might be in somebody's data center in an automotive company or perhaps in a small engineering firm, you're going to have a need for a certain number of compute nodes, right, that are going to run the HPC jobs. You're going to need some kind of scheduling software to run all the jobs on that node in a hopefully efficient manner. And these are job schedulers that you might be familiar with, LSF, SunGrid Engine, Slurm, Torque. There's lots of them out there. And so for those, you need head nodes to run the schedulers. You probably, if you're in the enterprise space, you're running commercial software that's provided by various vendors in the space, CAE tools, for example. So you need some license management capabilities. You can deploy all of this in the cloud really as you had previously done in the data center. The difference, of course, is now that cluster becomes scalable and automatically scalable if you put automation in place. So the more jobs you add to the queue, the more it scales up. When jobs drain out of the queue, it scales down automatically. You can also, as I said earlier, create that shared file system on AWS. If you're interested in using traditional schedulers, I mentioned a few before, LSF and SunGrid Engine and Torque and so forth. We do have an open source project called CFN Cluster. This is a CloudFormation template, and it will create for you in your VPC an HPC cluster that has the head node for your scheduler, that has the right automation to, to actually monitor the depth of the job queue and add nodes and subtract them as needed. And it can create a shared file system for you if you need it. So CFN Cluster has been very, very useful for migration of legacy HPC workloads to the cloud with minimal disruption, right? Really creates your HPC cluster automatically. HPC as code, if you will. Alternatively, if you want to be more cloud native, think about using AWS Batch for high-performance computing workloads. AWS Batch is turned out to be a very powerful approach, for example, in the life sciences community, in other areas where you have the need to scale very, very large. It's built around containers, so the use of container technology can really help with the efficiency of HPC workloads. And additionally, it integrates extremely well with Spot. So we will have sessions through the week covering Batch in more detail. But if you're interested in running HPC on AWS using more cloud native methods, then AWS Batch is absolutely something to look at. Now, for enterprises that are working in a hybrid environment that have on-premise resources as well as cloud resources, managing those resources and managing the inventory, if you will, the patch levels and so forth can be challenging. So another thing to consider here is EC2 Systems Manager, which continues to evolve its capabilities and can be used in these hybrid environments to help to manage these mixed workloads that are very common in the HPC space, where some applications are running on-premise, on legacy IT that have not yet been migrated, other workloads are running on the cloud. There are actually many ways to bridge that divide. IBM, for example, with their Spectrum tools, Spectrum compute tools, which are built on LSF, can also help with these hybrid environments. There's many, many choices out there to help you manage hybrid environments. I want to spend a little bit of time now and talk about graphics, because you can't really talk about high-performance computing without talking about high-performance graphics. And the reason for this is because applications that are used in enterprise, that are used in, let's say, energy sector or automotive, it's really about pre- and post-processing in addition to the HPC compute. I want to use a desktop application to create the model. I want to simulate the model. I'm going to get a 3D visualization as a result. Maybe the airflow over my wing or something, and I want to look at that graphically. So that full HPC environment is really enabled through graphics on the cloud. So there's a number of options here. There are partners who offer remote desktop capabilities. We offer remote desktop capabilities with our DCV product, with AppStream. There are vendors that offer completely managed solutions for this, like Rescale, that will help you to manage your HPC compute working with third-party ISVs. But a critical enabler here is access to GPUs in the cloud. And GPUs in the cloud can be delivered in two fundamental ways. One way is for you to launch an EC2 instance that has GPUs associated with it already. So this would be our P3 instance, for example, right? That has an NVIDIA GPU in an instance that has a particular number of CPU cores, a particular amount of RAM, and has GPU technologies. And that's useful if you need to have access to that NVIDIA GPU. You've got some CUDA code, you've got graphics drivers and so forth, right? The second way to get access to GPUs in the cloud is using Elastic GPU. Elastic GPU is intended for graphical applications. For example, applications that use OpenGL for the graphics rendering. Now, using Elastic GPU, you don't have to constrain yourself to a particular instance type like the P3. You can deploy on your C4, your C5, R4, even something like a P2 or P3, and attach graphics capabilities to it, right? So this is enabled through Elastic GPU. You launch your instance type, you attach to it an Elastic GPU. That Elastic GPU handles the graphics processing through OpenGL, and that accelerates the application. You'll want to test with your application, whether the ISV supports it in terms of the graphics libraries that they're using and other capabilities they may need, whether you would launch on something like a G3 with its NVIDIA GPU or the Elastic GPU that accelerates OpenGL. But it is there, it's capable, it's very performant, in fact, to do this. So Elastic GPU, again, to summarize, you can use Elastic GPU to deliver graphics capabilities to instance types that otherwise don't have them, right? So even an X1, for example, could suddenly have GPU graphics capabilities. Much more cost effective than choosing a one-size-fits-all GPU-accelerated instance. Desktop application streaming is a little bit different, right? So I described the use of G3 and I described the use of Elastic GPU, and those give the ability to have a GPU-enabled desktop, for example, right? I want to create a remote desktop environment using DCV, for example, or using some other remote desktop protocol. I have complete access to the operating system. I run my applications. In the case of AppStream 2.0, this is the ability to deliver graphic applications in more of a browser environment. So let's imagine, for example, that I am a IT administrator at an automotive supplier, perhaps, and I've got lots of engineers in the organization. Maybe I've got third-party contractors and collaborators, and I want them to have access to the tools that they need to use. So design and engineering tools, maybe for doing that modeling, right, SolidWorks and so forth. Maybe I want to give them access to simulation capabilities, maybe Ansys software or other software to run those big fluid simulations or impact simulations. And I want to give them access to the graphics on the back end to view the models or integrate them or whatever I need to do to have that complete design and engineering environment. So I have two choices. I can either give them the remote desktop and give them license keys and so forth to run all that software as they wish in their remote environment, or I can more closely manage it by using AppStream to deliver to those customers only those applications that they are authorized to use. So it's a thin client. It's a browser experience. AppStream 2.0 does allow you to share the data from one application to another, but you're really delivering just the applications that you've chosen to deliver through that environment. It can be much more secure, it can be much more cost effective than managing desktops. And it does have support for a wide variety of graphics needs. Again, based on the Elastic GPU concept I mentioned before, it offers a general purpose instance type, compute instance type, memory optimized, really choosing a selection of graphics and compute capabilities behind the scenes that you need to deliver the applications to the end users. And we are finding some really great use cases for AppStream 2.0. For example, in training simulations used in offshore oil rigs and so forth. We're also working closely with ISV partners that have graphically oriented tools, such as you see here. So to summarize, HPC, that term, high performance computing, means a lot of things to a lot of people, as I said. From our perspective, HPC is anything that requires lots of compute that may or may not be associated with lots of storage, right? So these range from large simulations in finance, engineering, life sciences, deep learning. But HPC is growing dramatically across industries. In many industries, there's a need to run simulations that didn't exist 20 years ago or 10 years ago, certainly in the financial sector, certainly in the engineering sector. Cloud has been incredibly enabling for some of these organizations to get the scale they need when they need them, and to right-size the compute for each problem, right? So flexibility of deployment, fast results, these are the goals of HPC in the cloud. These are the benefits that it delivers. And the last thing I wanted to emphasize again was that graphics is incredibly important for these HPC applications. It's not just about compute. It's not just about delivering the same kind of batch jobs that you had previously on premise in a faster, more efficient way in the cloud. It really is about rethinking the entire HPC workflow using cloud, graphics and compute and storage. So with that, I appreciate the session here today. I've got a few more minutes here for questions if you have them. I'll also stick around a little bit after, and we can go deeper on specific questions you might have. Thank you.